It is time to take the journey from decision trees all the way through random forest and gradient boosting to XGBoost. We have coded these machine learning algorithms. Now let's take a look and try to get a conceptual understanding. Okay, let's start with decision trees. So, as mentioned, decision trees is like a game of 20 questions. Each round, the data is split in half. Splits are made by determining which split will give the best score each round. The trees stop splitting when a desired level of accuracy has been reached. Since trees can keep going, they are prone to overfitting. Solutions to the overfitting, that is, can fine-tune the trees, something we'll look at, or combine them into ensembles. Before doing that, let's take a look inside a decision tree to see how it's actually built. So this is from the census dataset, and it has a max depth equal to 2, meaning that it only goes 2 levels or 2 branches before giving final predictions. Okay, let's start at the top of the tree. It says marital status, married civic spouse, less than or equal to 0.5. The idea here, I think, is that if you're married, maybe it's a 1, and if you're not, it's a 0. Okay, so what it's doing is it's splitting the data based on this. Okay, and you can see where it says value, it says like, hey, 18,000 plus, I believe then because it says class 0 would be unmarried and close to 6,000 would be married, and it splits it into this true and false. Okay, go down to the second level. These are called nodes, and you can see that the second level, they're using both capital gain and the education number of educational years to find another optimal split. Okay, and then if you go all the way to the bottom, those are called the leaves, and those are where the predictions are made. So if you look at the far left one, the green one, where it says Gini is 0.093. By the way, closer to 0, the better. Gini is a measure of impurity. And so what it's saying is that, of those, the predictions are that 12,304 of these, this group would all be class 0, meaning I believe they make less than 50,000. These are people with less than a capital gain of 7,073 and who are unmarried. So, and again, Gini, it's not quite percentage, but you could think of it like that. Maybe that one's about 90% right. You can see there's some variation in Gini across the board. The point here is not to understand this in depth, it's just to get a general idea of how decision trees actually work behind the scenes. Okay, let's take a look at random forests now. Random forests combine many decision trees, 100 by default. Trees are bootstrapped, meaning sampled with replacement. Okay, let's get a sense of what that means by looking at this image here. So here we have some original data. It's all these different colored points, and these are like individual rows, okay? So if you look at the far left underneath, it says classifier, okay? That is a decision tree. And what it does, it selects individual rows from the original data. It does not select them all necessarily. And what bootstrapping is that every time it selects one, it puts it back in the original before selecting another. So you can end up with repeats. If we look at the far right one, you can see there are more blue rows in the bootstrap sample than there are in the original data. The reason for this technique is so that the decision trees have diversity. If the decision trees were all the same, there would be no point in doing this because you would get the same result as one decision tree. Okay, randomness is involved with choosing the rows, bootstrapping, and the number of features columns to consider when making tree splits, so they don't actually use them all. Again, that allows for more variation and diversity. Since the decision trees vary, they give different predictions. The random forest takes the average of all trees to make a final prediction. Pretty cool. Random forests use bagging, which is bootstrapping plus aggregation. Let's look at this image one more time. Just the last piece, the aggregating. It simply is going to take the average of all the trees if it's a regressor, or the majority if it's a classifier. Okay? And so bagging is short for bootstrap aggregation. Aggregate means to combine in English. Bootstrapping is a statistical term. You guys may have heard the historical term. I think was it Horatio Alger, or someone pulling themselves up by their bootstraps. Okay. Anyway, let's take a look at gradient boosting now. What is this? Random forests are no better than individual trees. Random forest trees do not improve with time, right? They're just the average of a bunch of trees. Gradient boosting trains on the heirs of each subsequent tree in the ensemble. Therein is the difference. Like random forests, gradient boosting combines many trees, but instead of bagging, they boost trees to make them stronger. Gradient boosting can turn a weak learner into a strong learner. Boosting has been shown to be more effective than bagging overall. Here's a little image comparing gradient boosted trees to random forest. You can see you have a single decision tree on the left. Gradient boosting, the idea is that each new tree learns from the previous trees, whereas random forest is just a combination of many decision trees. And here it is again using a different look. You could say that bagging goes in parallel, where you're kind of like each tree is made from the original data set, whereas boosting is sequential. It's an evolution from one to the other. So gradient boosting is trained on the residuals. Gradient boosting trains on the residuals. The residuals are the difference between the predictions and the test set, right? This is like the error, like this, what the scoring metric gives you. So, this is just a way to look at it. Like, here's predicted on the left, predicted values for revenue. On the right side, it's showing the residuals. The residuals, basically, it's giving you the value, the distance from the points to the line, okay? So if you look at like the far left yellow dot, let's say it's at about negative 0.75, that means it was 0.75 under the, the actual value. If you look at the far right one, it's maybe about a 1.25, that means it's a 1.25 over, and those are the residuals, the difference between the predictions and the actual. The prediction, here would be the line and the actual would be the points, but you get the same number. Here's another one. It's almost a little trickier to look at. So it's like the subsequent iterations. If you look at the top left, you see where y equals 0. If you follow that, they didn't put on the right side. You follow that. Okay, so it's always 0 on the right side. It's like not quite in the middle. It's a little closer to the bottom. And the idea would be that the red, say, line is kind of like the prediction, and then these clusters of data points are some, there's a distance that they are from the red line. And so you can see each round what happens if you look at where it's 0, which is always right here, the data points get closer to it because the new line, this one, the new red line each round, is created based on the residuals. Okay, so it starts to get better over time. So how can gradient boosting be improved? We're looking at the evolution of decision trees here. Can it be faster? Can it be more accurate? Can it have more hyperparameters? That's what you use to adjust the individual trees. And you could say the overall model too. Yes, with XGBoost. So XGBoost in effect is a culmination of decision trees and gradient boosting. Extreme gradient boosting that's what XGBoost stands for, okay? It's faster than gradient boosting. Gradient boosting, by the way, there are gradient boosting algorithms like gradient boosting regressor, but XGBoost performs better pretty much always. It's usually more accurate than gradient boosting, as mentioned. And it includes unique hyperparameters to handle null values and imbalanced data, which is nice. It includes alternative-based learners beyond decision trees. It's kind of a fun topic. Has won many Kaggle competitions, which is proof that it's a successful algorithm. It's not just like people using it in research. It's competed against other models and won. And it's arguably the best machine learning algorithm for handling tabular data, meaning rows and columns of numerical and categorical data overall. That's what we look at in this course. I mean, you've seen it doesn't always produce the best results, but on average, if I had to pick one model to use, it would be Xgboost. So here's just a little Xgboost kind of technical visual. It's got parallelized tree building. That's for speed on computers. Tree pruning using a depth first approach. Cache awareness and out of core computing. Regularization, the automatic regularization, right? Highlight that one to avoid overfitting. That has that automatically, which a lot of the others don't. Efficient handling of missing data, an inbuilt cross-validation capability. Okay, so what are some facts about Xgboost? It's famous for winning the Higgs boson Kaggle competition to confirm the existence of the Higgs boson, which is also known as the God particle, to confirm the standard model of physics. Scikit-learn wrapper, new as of 2018 for the XGB classifier and XGB regressor. That's what we have been using. XGBoost has their own random forest, the XGB RF classifier and XGB RF regressor. Those are getting better over time. XGBoost uses sparse matrices to speed up computations, performs 10 times faster than gradient boosting. Finally, XGBoost takes advantage of hardware software components like cache and parallel processing to maintain an edge in speed. Finally, here's some Xgboost links provided with the slides here. There's the official documentation. You can get the official info. There's a nice little tutorial here that they have. You can get the original paper. Now, these are all pretty technical, okay, but just giving these out. Nice little YouTube link that you can watch. More info on the hyperparameters and this analytics video blog. And there is the XGBoost book GitHub page, which I wrote, that's provided here, that includes a lot of IPython notebooks with XGBoost code. Okay. And who is this? This is Tianqi Chen, the founder of XGBoost. You know, it's really a seminal accomplishment in the world of machine learning. So, happy coding.